Good evening, everyone. Welcome to the final session of the Siyanqoba training program for school learners. This is the senior session, number 10. And I want to take this opportunity to thank all of you for coming regularly to all the sessions. And I trust that you have learned quite a bit over these last 10 sessions. I do plan to have other sessions privately, but I will give you more information about that later. All right, so if we can go on immediately to the matter at hand. Today, we are going to do a number of problems. Many of them are what we call logical problems. And they're very nice problems because you don't require too much of mathematics. But they do require a lot of thought and strategies to solve them. So I would not be writing too much, but hopefully you can listen very carefully. Please pay careful attention to follow the logic in the arguments. Not all of them are logical problems, but many of them are. All right. So, Khorsod, can you see the screen?
Yes, Prof, I can see the screen.
Okay, thank you very much. All right, so let's go to the very first problem. This problem reads, a bag contains 65 marbles of the same size. There are 20 red ones. Let's just make a record of what we've got. The red, 20, green, 20, and blue, 20. And you got 5 which are yellow or white. We'll just say 5 others. All right, so Ahmed removes marbles from the bag without looking. So he's got all these marbles inside a bag here, and he's just picks those marbles out without looking. And he keeps taking them out, maybe one by one. And he says, what is the smallest number of marbles that he must remove to ensure that he has 10 of the same color? All right. So that means, what is the smallest number of marbles he must remove to ensure that for certain he must have 10 of the same color? So what we have to do is to take the worst possible case and say, okay, he doesn't get 10 of the same color until such time you keep coming to a situation where he's forced to take 10 of the same color. Okay, so let's take the worst possible case. You can take, for instance, he's got 20 red ones. So you can take 9 red and you can't take any more, all right? Because then you will have 10 of the same color. So I'm taking the worst possible case. Then you can take 9 green. And then he doesn't take any further green. So he's still not achieving the purpose. Or you can take 9 blue. And he still would not have got 10 of the same color. And then you can take all these 5. None of them will have 10 of the same color, obviously, yellow and white. Okay. But now, at this stage here, is collected 27, 32 marbles. Now, the moment he puts his hand in the bag, these are gone, and he'll have to take one of these now. Any one. The moment he takes one, you'll have 10 of the same color. So in other words, he takes 32 plus 1. On the 33rd one, and that's the first time you can be assured that he will have 10 of the same color. And 33 is the answer. The moment he takes one more, you will have 10 of the same color. So that is the answer to this problem. That's the smallest amount that you can take to ensure. You see, you must make sure that he has the same color. Okay. The next problem, let's go to the next problem. Problem number 2. Here, this problem says, on the chessboard, a knight starts from a square and returns to the same square after making several moves. All right, so a knight starts from a certain square and returns to the same square. So I don't know whether you know how a knight moves. But if you don't, it moves like this. A knight moves in the L shape. It goes 1 in any direction, and then 2 more in the opposite direction. So it always goes in the form of an L. See? Say 1 this way, 2 this way, 1 that way, 2 this way, 1 that way, 2 that way. So it's always 1 in one direction and 2 in another direction. Okay, so let's see what happens. It says here that the knight starts at some square. Say it starts here, right? Now, it returns to the same square. So after making several moves, show that the knight makes an even number of moves. And that's very interesting. Okay. Now, you can move from here to here. Okay, now it doesn't really matter. You see, when this knight moves according to the way it's supposed to move, like you look in this diagram, it moves one that way, that way. It goes from white to black, right? And from here now, if you want to make another move, you can go say 2 that way and 1 that way, and it goes black to white. And then you can go from here to here, from white to black. Now, it goes all over the place and it comes back to the original square. So, like in this diagram here, it starts with white and it ends with white. See? Now, after the first move, it becomes black. And after the second move, it comes white. So in other words, after 2 moves, it comes to the same color. Right? The first move, it goes to the opposite color. The second move, it comes back to the same color. And to come back to after 1 move beyond that, it's a black. But again, after 2 moves, it comes back to the same color. So it comes back to the same color always after 2 plus 2 plus 2 plus 2. So an even number of moves. And there it lands here. So it'll be some point or the other, it comes back to its white after 2 moves. So you can see it's going to make an even number of moves. So it comes, the argument is that it comes back to the same color. It need not be white, but it could be black. It comes back to the same color after every 2 moves. And since it comes back to its original square, right, which is the color that it started off with, then it has to make an even number of moves because it's 2 plus 2 plus 2 several times until it comes to the last one. Okay, so that takes care of that problem. Let's go to Question 3. The children at a school fun day had to guess the number of marbles in a jar. Right. So I don't know whether they still do that. When I was young, they used to have this kind of a interesting thing. You guess, like a number of marbles, and people this it's a nice way of raising funds, a fun way for maybe a school or something like that. And then people will come, they say, let me try. And they say, okay, for whatever, the 1 rand, they pay, and they try to guess the number of marbles in a jar. Now, the first prize went to Emily, who guessed 125 marbles. Okay, so Emily, she said 125. Okay. The second prize went to Cassandra, so you could just put E here, E for Emily. And she was first. First prize went to Emily, she guessed 125. Second prize went to Cassandra, who guessed 140. I'm going to put these in a straight line. 140 is this way. Cassandra is 140. Let's see. And she got second prize. The third prize went to Sigrid, who guessed 142. So she was on this side now, and she put 142, and we'll call it Sigrid, and she's third. I'm just recording the information. I'm taking all the numbers and putting it on the number line. Let's see just now why. And the fourth prize went to Rina, who guessed 121, so she was up here. So she said 121, and it's Rina, and she was fourth. Right. Now, how many marbles were in the jar? So that's very interesting. How many marbles were in the jar? Okay, let's look at the first and the second. Right? Emma, or whatever her name was, Emily, she was closer to the guess than Cassandra because she came second. Now, what do you mean by closer? You have to take the halfway number between 125 and 140. That's the average of the two. So halfway between the two is 265 divided by 2. So it's 132 and a half. All right. So Emily, she guessed she was first. So the actual number of marbles, the winning marbles is somewhere here because she was the first. So let's see what the possibilities are. So the winning marble could be 125. She might have guessed it exactly. Or 126, 127, and so on, up to 132. So that's where the winning marble is. Where Emily came first, you see. Cassandra, she missed it. So she's somewhere on that side, and further away from the actual one. So the winning marble is here somewhere. Okay, now let's look at the third and the fourth. So you got Rina is 121, and Sigrid or something like that, her name is, she's 142, and Sigrid was closer. So you got 265. Oh, you got 265 again. So it's 132 and a half. right? So cigarette was third. So the answer is between, no, it's 142, it's 163, I'm sorry. 263 here. So it's 131 and a half. Right. So cigarette was third. So the winning marble would have been here bigger than 131 because cigarette was closer to the winning marble. So the numbers bigger than 131 are 132, 133, and so on. And the winning marble is here. So now you can see the winning marble is from 132 onwards and is also from 132 below. So the only number in both cases, because that's where the winning marble is, not the winning marble, but the winning number, the winning guess, the number of marbles, right, is going to be there and it's also there. So the only number which is in both is 132. So the answer is 132. You see, there's no mathematics here. There's no X and Y and so on. It's just pure logic. Mathematics trains us to actually think logically. That's one of the greatest assets of mathematics. People who can think logically are usually people who are good in mathematics. But sometimes people who are good in mathematics, they need not be able to think logically. But the really good ones are those who can solve logical problems. All right, because it is all about thinking and arguing so that you come to a right conclusion using the evidence that is there before you. Okay, we now get on to the next problem. Now this problem here, it says Esther, Basta, and Custer. Oh, all right. Now there are three villages. Oh, these are three villages, A, B, and C. So that's very useful. They named them A, B, and C, which is nice naming. So these are the villages. I got these pictures on a picture of the three villages as shown in the diagram. The straight lines represent the only roads joining the villages. So this is all these are roads, and the figures give the distances in kilometers between the villages. So these two, they are 7 kilometers along, and this is 8 and so on. So if one wants to go from this point to that, you can go like that, because they're the only roads, or you can go like that. Okay, so you can choose which route he wants to take, and evidently you will choose the one which is shorter, so you can say one is better. So so the people who are living along these roads, they can go from one town to the other along these roads. Now a new fire station is to be built to serve all three villages. So you've got a fire station, it's going to be built somewhere, and it's going to be on the roadside. So it's going to be somewhere along this road here, at such a position that the greatest distance that the fire engine has to travel along the roads in an emergency at any one of the villages is as small as possible. Right? Now, where should the fire station be positioned to locate your point on the diagram? Now, locate your point on the diagram and explain why no other position is satisfactory. Okay, we have to understand this. You want to place this fire station, like suppose now I want to place the fire station here, right? Then I can see that well, if I place it there, then what are the distances? You got, okay, I should say maybe 4. Sorry, say it's 4 kilometers from Costa. Right. Now, this fire station, how far is it from Costa? It's 4. And how far is it from Besta? It could be, if you go this way, it's either 12. And if you go that way, it's 8 plus 7, which is 15, right? So you're not going to go the long distance. So fire is going on, so you choose the 12 distance. If the fire is at B, right? And then if you go this way, and then if the fire is at C, if the fire is at C, the fire is at B, it's like this, and if the fire is at A, so this is from near 4 so it's 8, right? Okay, now you want the greatest distance to be as small as possible. So here the greatest distance is 12, but you want that to be as small as possible. All right. So it can be better 12. If I chose it here, then I've got the greatest distance is 12. If I chose it 4 kilometers from Costa. Okay, so how are you going to solve this problem? Okay, I think the best way to do it is to find out what the middle distance is. Like for instance, the middle distance from ACB, I've got 8 here and I've got 12 here. So what is the midpoint between A and B along the roads? You got 12, 8, so that's 20. So if you put the fire station here, then it's at equal distance because you got 2 here and you got 10 here. So it's 10 this way and 10 that way. So you can put it here, it's equal distance, and then to that point, now it's 2 from here to C and 2. So in this case here, the distances, you got 2 from here, 10 from there, and the distance to B is either 10 or 17. We'll take the smaller one, and that is why the midpoint helps a great deal. So in this case here, it is 10. If you chose the fire station along AC, all right. Okay, that's a halfway point between this and this. Now let's take the halfway point between that and that. So you got 7 plus 8 is 15, and now you got, it'll be 7.5. So you got half a kilometer here. So you got 7.5 this way, and from here to here you got another 7.5. There's 8 minus half. So in this case here, you got 7.5, 7.5, and to this and to this, and the distance to C is 7.5, but the distance to B is a half. Now, so and the greatest distance here is 7.5. So this point here is better than that. So you can eliminate that one, right? This is an improvement. And then if you work out the greatest distance between that and that, you take the midpoint, you'll see that is, you can try it, but the final answer is 7.5. Because that last pair will give you something which is bigger than 2.5. So the greatest, you have to build the fire station here, and they tell you, locate your point in the diagram, as I've done. That's your answer. And explain why no other position is satisfactory. All right, we have done all that. So let's go on to the next problem. Okay, here you've got 100 soldiers are in a detachment, and every evening, 3 of them are on duty. All right, so you've got some kind of a guard duty. Maybe all these soldiers are in some kind of a camp or something like that. And you've got 3 people who are on duty. Okay, let's just put them in their guardhouse. So you got these 3 people are here, and they are on duty. But there are 100 soldiers altogether. Okay, and 3 of them are chosen to be on duty. Now, can it happen that after a certain period of time, some soldier has shared duty with every other soldier exactly once. All right. So again, let's understand it. Can it happen that after a certain period of time, some soldier has shared duty with every other soldier exactly once? So the question is, can it happen? Now, in questions like this now, we often assume the opposite. You'll see a lot of cases like that. You assume something which is different from what you are trying to prove. And that's a very good strategy, because what happens if you assume something which is different from what you're trying to prove and use that as your starting point and say, okay, suppose this is true, and you keep going until you come to something which is not true. Then you will say, so you start off with some assumption, and then you'll argue logically and come to something which is not true. Right? Then you'll say, what happened? Why? I'll come to something which is not true. So it means that this assumption is false. Right? Now, once you come to that, you can say, therefore, the assumption is false. And since there are two possibilities, then you will know what is true, you see? And that way you can verify some statement. So the statement is either true or false, and you assume it's false, or whatever, you assume the opposite, and then you keep coming to something which is impossible. Then they say, look, why is it impossible? And then they say, that's because whatever I had assumed in the beginning is not true. So therefore, then you'll know what is true, you see. So now this is a good example where you can apply this logic, because it says that you say, can it happen that some soldier shares duty? So you say, suppose such a soldier exists. In other words, what does this mean? So there's a soldier here, he's one of these 100 people, and is shared duty with every other soldier exactly once. Okay, so there he is sitting in the guardhouse, and he gets two people, and he's shared with them, right? Now, the next time around, he's going to share with, you can't use either of them, because you must share with them exactly once. So you got two new people, right? And then he keeps going on like this. So the first round, he got two new people. And is it possible that you're going to have two new people all the time? It's not possible. When you come to the 98th, this is two, and you got four people, and the 97th and the 98th, this is the first and second, he shares with them, third and fourth, he shares with them, comes to this. Now he's stuck because he's got only one other person left here. He is one of the 100. He's only got one guy here, and he cannot share because he has to take one from the others who he has already shared with. So, so it's not possible, right? So this is a contradiction. We are saying such a person exists, so and this person cannot exist in this case, at this level. So therefore the soldier, the assumption is false, and therefore we say the answer is, can it happen? And we said, yeah, we said, yes, it can happen. And you come to something which is impossible. So therefore the answer is no. If the answer was yes, you come to something which is impossible. Therefore, the answer is no. All right. So that's a good example of a logical problem. All right. So let's go on to the next one. Okay, we're going on to question 6 now. What does question 6 say? There are 5 animals, A, B, C, D, E, are either wolves or dogs. So you got 2 types of animals. That animal could be a wolf or it could be a dog. Now, dogs always tell the truth. Okay, now this is an hypothetical, impossible thing. So, but whatever it is, so dogs always say the truth, always. They don't ever speak lies. And the wolves always lie, always lie. Right. Now, these 5 animals each make a statement about themselves because the one animal says, B is a dog. And the other one says, C is a, C says D is a wolf. But you don't know now what these guys are, whether they are dogs or wolves, A, B, C, D, E. All right? So you don't know. So again, now this is a problem regarding where you can apply contradiction and how you call that contradiction, by the way. Proof by contradiction is what I did before. And proof by contradiction, the starting point is assume something and come to a false conclusion. All right, now here you got, A is either a dog or a wolf. So you assume something. So I'm assuming, suppose I assume that A is a dog. Right? I'll try to see whether I can get to a contradiction. Right? Okay. And then if I do get a contradiction, then I can make the conclusion that A is a wolf. Right? So let's start with A is a dog. So A is a dog. So I can put D here. Right. Now A is a dog, right? Now because it's a dog, it speaks the truth. And it claims, A claims that B is a dog. So A speaks the truth. So B is a dog. Now let's see what B says. So B also speaks the truth. B says C is a wolf. Right? And B is speaking the truth because we came to the conclusion that B is a dog. And he says C is a wolf. So that's true. C is a wolf. And what does C say? C says D is a wolf. Now C is a wolf now. See, so he's a liar. And he says D is a wolf. So he's lying when he says D is a wolf. So therefore D must be a dog. Right? Okay. Now, since D is the dog, let's see what does D say. D says B and E are of different kinds. So he says B and D says B and E are of different kinds. Oh no. Oh yeah. Now E claims that A is a dog. E claims that A is a dog. So, but now A is a dog. That's quite right. So if E is claiming that A is a dog, he's speaking the truth. Right. Now, what does D say? D claims that B and E are of different kinds. E says that they are of different kinds. Now, that's not true because we came to the conclusion that B and E are both dogs. So this came to a contradiction. See, you get a contradiction at that level there. So our assumption is false. The assumption that A is a wolf, that A is a dog is false. So we can eliminate all these. Okay, so now we know that A is a wolf. Because by assuming that A is a dog, we came to a contradiction. But the question is, how many wolves are there? Okay, so let's start now. A is a wolf. And therefore, he speaks lies. Right? He's a liar. Now, A claims that B is a dog. So that's a lie. So B is actually a wolf. And now B is a wolf. So B also lies. What does B say? B says C is a wolf. So that's a lie. So C is actually a dog. Because B is a wolf, he lies. So what did B say? B says that he's lying, and he says C is a wolf, therefore C is a dog. And that's what I've got here. So now C is a dog, so C speaks the truth. Now C, what does he say? C claims that D is a wolf, so he speaks the truth. D is a wolf, right? He's speaking the truth. But D now is a wolf, so therefore he is, whatever he said is a lie. So D, whatever he said is a lie. He says that B and E are of different kinds. B and E, no. Yeah, what does E say? Oh, yeah, I have to see what E says. E says that A is a dog. That's what E said. E claims that A is a dog. And you look at A, that's false. So E is lying. So E must be a wolf. All right. And now let's go to what D says. D says that B and E are of different kinds. And if you look at B and E, yeah, they are not of, they are both wolves. So D is lying, and we did conclude that D is a wolf. So this is fine. So this is where we are. And how many wolves are there? The answer is 4. It's actually great fun, all this. You know, I'm sure you'll enjoy it because it's all following an argument, and eventually you come to something. Now, we had 2 examples where you make a false assumption. You don't make a false assumption. You make an assumption. You don't know whether it's true or false. You make an assumption, and you come to something which is not true, and then you will say your original assumption is false. That's what happened. I started with A is a dog. I came to something which is a contradiction, right? Therefore, A turns out to be a wolf, and then I continue in that line. Okay, so let's just get on to the next problem. Here, I think we've got on to problem number 7. Okay, so you got a long story here. Question 7. So you got Jack, John, and James are identical triplets, right? They all look the same. It is impossible to distinguish them by appearance. All right. Jack always speaks the truth. So Jack is a truth teller. And John and James always lie. Well, this is Jack. Let me just take that out. Say Jack always speaks the truth. And John and James always lie. Okay. You know that the triplets are between 20 and 30 years old. So, in other words, what is true, because you know that, they are between 20 and 30 years old, 20 and 30 included. So, the triplets are either 20 or 21. They're all of the same age, obviously, the triplets. So, their age is one of these. '20 and 30 included. So, we don't know which one. Okay. Now, one day, you meet 2 of the triplets. Right now, you don't know which 2 you meet because they're all identical. Anyway, you meet 2 of them. I know we don't know what they are, so we are calling them A and B. So what does A say? A says, we are between 20 and 30, 29. So this is what A says. He says we are between 20 and 29. 20 and 29 are included. So A says this 20, 21, 22, 23, all the way up to 29. This is what A says. Now, you don't know whether he's speaking the truth or whether he's lying. He says that, right? Okay, so that's what A says. Now, B, what does B say? B says we are between 21 and 30. He says 21. B says that. But he also says that one of us present is lying. Now, this is where it gets tough. Right? One of us is lying. He says one is lying. So it means exactly one is lying and one is speaking the truth. Okay, now we don't know whether A is lying or B is lying, but again, we'll try to prove this by contradiction. So we'll say, let's have a look at B, right? And we ask ourselves, is B speaking the truth or is B lying? Right. So suppose we say B is lying. If we can come to a contradiction, if we can come to a contradiction, then something which is impossible. We know this, but this one here, the question mark around this. But now we are saying B is lying, so this is a lie. And this is also a lie. We don't know about that guy. Okay, now suppose B is lying. That's a lie. But now I like to focus on this. He says one of us is lying. So what B is saying is that we are, one of us is lying and the other is speaking the truth. Right? So now B certainly is lying. Right? So, and he says one of us is lying, but that's a lie. So therefore it means that it is not, you don't have that. If you had that, then that would be true, you see. So you don't have that. So what it means is that either both are lying or both are speaking the truth. Right? Now you can't have both speaking the truth because there's only one truth teller. So and this is where it becomes very tricky. So he says one of us is lying. So this pair is not LT because this would have been the, if you said that, then he's speaking the truth. But we're saying he's speaking his lies. It's not LT. So therefore, it's either TT, only three possibilities, TT, the other two, or LL. Now it can't be TT because there's only one truth teller. So that's off. So therefore, it'll be LL. Right, so if we are assuming that, this is the assumption, remember, we're assuming that B is lying. And we are arguing this, and we come to the situation where, with that assumption, that both of them are lying. So now that means that A is lying. See? Which means, therefore A is lying. And B is also lying. A and B are lying. because we are assuming that B is lying. Now, from here, both, because we come to the conclusion that both are lying, so therefore A is lying. Now, if A is lying, A, now this is true, you see. So if this is a lie, that means that the age is 30. The age is 30. Now B is lying, but B says that one of us is 30. So B is not lying. So now you have a contradiction here because A is lying, so therefore the age can't be here. So it has to be 30. But the moment you say their age is 30, B said that one of our ages are, it could be 30. So that means B is speaking the truth. But we concluded that by assumption B is lying. So now we get an impossible situation here, because you can't have both of these are true, right? You can't have their ages are 30 and not 30 at the same time. So this is false. So we come to a contradiction now. So this is where the contradiction is, right? So it means the original assumption here is false. The original assumption being that B is lying. So let's change that, and I'm going to just rewrite all these conclusions. It's not very easy to follow, but you, as I always tell you, you must go back and try to reconstruct the argument. But the starting point is, and that's very important, you must write this down. In this thing, yeah, the starting point is assume B is lying. Right? Then only you will come to the, it's a tough, very tough problem. I struggled with this one. So when I came to only this, when I came to the contradiction when B is lying, then I knew I'm getting somewhere. So therefore, that is a contradiction. It means that B is speaking the truth. Right. So when he says that one of us is lying, it means that A is lying then. Right? Because he's speaking the truth. So the other guy must be lying. So therefore, if A is lying, that means the age is 30. Right? Because A is lying. So that's their age. And if you check to see it, you can see B is speaking the truth because he says that one of these, the age is between 21 and 30. So the answer is, how old are they? The answer is 30. Now this is quite a mouthful, this argument, this logical argument. Again, it's all about contradiction. We are only looking at those examples. Because these logical problems, they're not always like this. Sometimes there are some other, I'm sure we'll come across some things where you don't have to prove anything by contradiction, but it's a logical problem. Okay. So let's go on. Okay. Now consider 5 not necessarily different natural numbers. Not necessarily different. So they could be equal. You got 5 numbers, maybe some of them are equal, maybe all of them are equal. But they say not necessarily different. Now Paul finds all possible sums of the 2 numbers at a time and gets 3 possible totals. Oh, okay. So you don't know what these numbers are. There are 5 numbers, but if the numbers are, say, A, B, C, D, E. Suppose the numbers are A, B, C, D, E, and then he works out the sums of 2 numbers. Because A plus B, or A plus C, or A plus D, or A plus E. He writes down all these possible sums, but he only gets three totals, although there are so many additions that take place. He only gets three totals. And the question is, what is the largest number? So A plus B is going to be one of them. B plus C is going to be one of them. They say, what is the largest number? All right. So the starting point here is we don't know what the largest number is, but let us order these numbers from smallest to largest. So we're giving names to them. Suppose the numbers are, and I'm going to put them in increasing order from smallest to largest. A, B, C, D, E. So you're going to have A, B, C, D, E, smallest to the largest. So A is less than B, but it could be equal because they are not necessarily different. So you could have B is less than or equal to C is less than or equal to D. Right? So now we want to know what is E. What is the largest number? Okay, now this is quite interesting. Now, if you got 83 here is the largest possible sum. The largest possible sum in the sequence here is the largest sum of two is D plus E. There's no sum which is larger. Then you take the second largest plus the largest, right? And we know what the sum is going to be. It can't be 57 or 70, or it has to be 83 because the sum of those two numbers is one of these, but it's the largest sum, so it has to be 83. Now, from here, now what kind of conclusion can you make? The conclusion you can make here, interestingly, is that D and E can't be the same. Now, what's the reason for that? Because if D and E are the same, then the sum of a number with itself will be an even number, right? And this is an odd number. So I can take out this less than or equal to sign here because I'm saying, by the way, when you say that, this statement like this says there are two possibilities. It could be that A is strictly less than B, smaller, or it could be equal. So whenever you have this, there are two possibilities. Always remember that when you got this. But if you leave it like that, then A is less than B. There's no other possibility. See? So we just said now that D is not equal to E. So I can take that equal sign out and I can I have that D is less than E. All right, so that's fine. Now let's have a look at A and B. You will have that again, for the same reason, you have the smallest sum is A plus B. That's the smallest sum, right? And that is equal to 57. So for exactly the same argument, you can't have A is equal to B because then A plus B will be even. So I can't have A equal to B even here. So I can remove that. Right. Now, okay, so what does this mean now? It now means that A is less than B less than E, right? Because A is smaller, strictly less than B, and B is strictly less than E. So it means that A plus B is the smallest. We know that's 57. And now B plus E will have to be 70. So B plus E will have to be 70. See? Oh, yes. Actually, I think you have A plus, this implies that A plus B must be smaller than B plus E. And this one here is 57. So B plus E is either 70, this is 70 or 83. Because there are only three possible sums. But if B plus E is 70, uh, E is the largest, then I'm missing something here. So A plus B is 57, right? That's fine. B plus E is strictly greater, so it could be that. But B plus E is also I got one other thing here. I got A plus E. I also got the A plus B. A plus B, A plus E. Yeah, you got A plus E. A plus B is smaller than A plus E. Yeah, you got A plus B is strictly smaller than A plus E, right? According to this. And therefore, if you cancel the E's, sorry, let's just get this thing right. It's very, very untidy. My apologies. You know, we mathematicians, we just write all over the place without considering that I've got an audience in front of me. My deepest apologies. So you got A plus B is less than that. And you also have that, therefore A plus E is smaller than B plus E because A is smaller than B, right? And you also have that A plus B is less than A plus E. A plus B is strictly less than A plus E. So which means that B is smaller than E. See? So B is smaller than E. Oh, which we already had. Okay. So this is 57. So therefore A plus E must be 70 or so A plus E is 70, 57 or 70. Right. But A plus E can't be, both of them can't be the same because otherwise you'll have this situation. Okay, so eventually you get to the conclusion that all these are the same. B equals C equals D, right? Because you only got three possible sums, right? So all of them are the same, and they all will be, because B plus C will be 30, 70, and they're equal, so all of them are 35. So that is what you got. You got all of these are 35, right? So B equals C equals D. They add up to 70, that's the even number, and they're all 35. So now you can say what these are. So B is 35, 35, 35, and that when you add D and E, then you got 83. So if D is 35, then E is 48. Right? So from here now, we needed to calculate E. So I've got D now. See, I've got D is 35. So therefore, you can say what E is, you simply subtract 35 from. So the answer is 48. It's a kind of a tricky problem. I got stuck also because I'm not sure exactly how to work with these inequalities. But you have to exploit this fact here and see how far you can go. All right. So the next one is question 9. If A, B, and C are three different numbers such that, okay, you got equations here now. This doesn't seem to be a logical problem. A squared minus BC is equal to 7. B squared minus AC is equal to 7. I'm rewriting these here. C squared minus AB is equal to 7. So you got three unknowns, A, B, and C. You got three equations, but they are not normal equations that we studied in school. Because you got a square there, it looks like a quadratic, and you got three unknowns in each equation, and so on. It's a very different type of set of equations which we from which we had any experience. So we have to figure out our own way of trying to solve these kinds of problems. Right? You have to figure out a strategy to solve them. Now, that's all that is given. But they say they are different. Okay, now that's useful. They're all different. Okay. So where do we start here? Now I can get let me try to get ABC all over here. So I can multiply by A right throughout to get A. Then I can get ABC here and I can get an ABC here. So I can get a common term right throughout ABC. But to get an ABC, I have to multiply right throughout by A. So the A cubed minus ABC is equal to 7A. Right. Here too, you've got a similar thing. You've got B cubed. If I multiply this by B right through, I get B cubed minus ABC is equal to 7B, right? And then here, I can multiply right throughout by C this time, right? And I get C cubed minus ABC is equal to 7C. The problem is to find A squared plus B squared plus C squared. Okay, so now, All right, so the purpose of doing this was we wanted to show that a cubed minus 7a is equal to abc. I'm making abc the subject of the formula, bring it to that side. I got abc again on the second one, so I got this is equal to b cubed minus 7b. And this is equal to c cubed minus 7c. All right, so now you got a cubed minus 7a equals b cubed minus 7b equals c cubed minus 7c. All right. I found a very easy solution to this, but I can't remember what it was. Now I have to go through the hard solution. Mm. Mm. All right. Now let's have a look at these two equations here. I got a cubed minus 7a minus 7b. 7a equals is equal to b cubed minus 7b. Now I can bring the b cubed to this side. I like to do that because then I'll get a difference of two cubes. And I know something about difference of two cubes. And bring the 7a to this side. And I have 7a minus 7b. Right? And now this is nice because I can factorize both sides. And here I get a minus b, a difference of two cubes. Right? Hope you know how to factorize that. You get it's a squared plus ab plus b squared. That is how you factorize the left-hand side. And here you got 7 into a minus b. On this side, 7 is a common factor. Now, a minus b, I can cancel. Now, you can't cancel on two sides of an equation. You must be very, very careful, right? You can't cancel xy equals xz. You can't say that implies that y equals z. You have to say if x is not 0. You can't divide by 0, you see, right? So if x is not 0, then you see, then you can cancel. Now I know that a is not equal to b because they say that all these are different. So therefore a minus b is not equal to 0. So I can cancel on both sides. Now I have a squared minus ab, a squared plus ab plus b squared is equal to 7. All right. So, oh, I see. Okay, now you got the a squared plus b squared. I want to find a squared plus b squared plus c squared. So this is 7 minus ab, right? But ab from here, ab is c squared minus 7. ab, if you bring it to this side, is c squared minus 7. Now you got 7 minus c squared plus 7, which is 14 minus c squared. And if you bring the c squared to the other side, c squared, a squared plus b squared plus c squared is 14. Yeah, this was the easy solution that I found because I had another one which was very complicated. So the idea is I just take two of these and make them equal, both of them equal to ABC. And then you can see by factorizing and canceling, you're allowed to cancel because there are three different numbers. And then once you do that, and the trick is once you come to this, you have to go straight into the third equation, which is c squared. You can substitute for AB because you have an equation where AB is present. All right, so that's the answer. Find the value of a squared plus b squared plus c squared. This is a good example of where you got three equations with three unknowns, and you don't have any strategy to solve them. And so I just suggested that you can put a, b, c right throughout by just multiplying by a and b and c, and see where you can get to. And that is what happened. When I got to this, then I could see I can move forward, I can factorize and cancel and so on. So that helped a great deal. Okay, so let's get on to the next problem. Okay, this clock works correctly, but the numbers are missing. And the clock has been rotated. This is really... So we don't know where the... I guess you all know what the how these clocks are. You know, you have normally your clock is facing nicely. It's 12, and you got 1, 2, 3, 4, all the way up to 11, 12. Right, but this one here has been rotated, so you don't know where the 12 is sitting. Right? And you only have these hour hand and the minute hand. And from that, can we make any conclusion? Well, I can see, you see, a clock. If the minute hand is at 12, to get to the hour hand, right? The hour hand has to move 5 minutes, and the minute hand moves 60 minutes in the same time. Right? So when the hour hand moves only 5 minutes, the minute hand moves 60 minutes, which means that the minute hand is traveling 12 times faster than the hour hand. Hour hand only crawls forward 5, and that goes 60, traveling 12 times the speed of that. So you must understand that. So here now, the hour hand has only moved 3 minutes. Has moved 3 minutes past. Let's give a name to this number here. 3 minutes past B. All right. So it means that 5 minutes will be 1 hour. It corresponds to 1 hour of the minute hand. So 3 minutes, 5 minutes of HH, hour hand, is 1 hour of minute hand. So 3 minutes of hour hand. Now this is, the hour hand has moved 3 minutes. Will be 3/5 of 1 hour. So that's 36 of the minute hand. So the minute hand has moved 36 minutes. And you can see here, you got the minute hand is just going one forward here. So there's 36 minutes, which means that this thing here must be 7. Because you got, this is the 36th minute. So this is the 35th minute. And the 35th minute is at the number 7. Right? And they ask you what is represented by the number A. So A will have to be 8. Right? A will have to be 8. And this is 6. This is 5. Like that. Okay, so it's interesting. You see, just by looking at the minute hand, it has moved 3/5 of what the hour hand would have moved from here to here. right? So if it moved 3 units, that means the minute hand would have traveled 12 times more than that. 12 times 3. That's the other way of looking at it. This minute hand has only moved 3 units from here, so the hour hand would have moved 36 minutes, 12 times 3. I worked it out 3/5 and all that, but it's just much better to say it's 12 times that. So the hour hand has moved 36 minutes, and therefore that can allows you to say that that is 7. So there's 8. All right, so let's just get on to the next problem. Tom was jogging at a constant speed of 10 kilometers per hour. Oh, okay, and we've gone to a distance time problem. So Tom was traveling at a constant speed of 10 kilometers per hour along a straight road. And you know, whenever I have a thing like that, you normally draw a diagram to just understand the problem. So let's draw a diagram. So Tom is traveling somewhere. Let's suppose he's going this way, and he's happily moving along at 10 kilometers per hour. And Jerry, jogging at a constant speed of 12 kilometers per hour, is 600 meters behind Tom. So he is also jogging, is behind Tom and is traveling at 12 kilometers per hour. How many, after how many minutes, the 600 meters, after how many minutes will Jerry take to catch up with Tom? Oh, this guy who wrote this problem here, he obviously doesn't watch cartoons on TV when he was small. I used to read them in comics. But Tom is the cat, guys, and Jerry is the mouse. It will be Tom who is chasing Jerry, and not Jerry who is chasing Tom. And Tom will be traveling much faster than Jerry. I mean, this fellow is a small little mouse. So they got this guy, he uses Tom and Jerry, but he doesn't know his comics. All right, so the point is he is traveling faster, 12 kilometers per hour, and he's traveling at 10 kilometers per hour. So he's traveling at 2 kilometers per hour faster than this guy. And so, in other words, to catch up with him, he has to move 600 meters. And his actual speed is relative to Tom is 2 kilometers per hour. It's as if Tom is standing still and he is moving at 2 kilometers per hour. Because the 10, 12 is it's like that. So he is catching up with him. In every hour is in yeah, he's traveling 2 kilometers per hour faster than this guy. So the question is now, how long will it take him? If he's traveling 2 kilometers, that's 2,000 meters in 1 hour and 60 meters, 60 minutes. And he has to, that's what his speed is. And he has to travel 600 meters in how many ways? So this is a proportion problem. 600 over 2,000 times 60 minutes. Okay, no need to multiply. Cancel the tens, cancel the tens, cancel that. So the 3 zeros go away. 2 goes into 6 3 times, and 3 times 6 is 18. So you'll catch up with him in 18 minutes. Yeah, the trick is You say, I'm sure he's traveling at 2 kilometers per hour faster than the other fellow. So it's as if the other guy is standing still and he has to cover 600 meters, right? And how long will it take him to do that? Okay, so the next problem, that wasn't a very difficult problem. The next problem is this one. Oh, okay. In a soccer tournament, each of the 6 teams played with the other teams exactly once. So you got 6 teams. I'm calling them A, B, C, D, E, F. I don't know what those names are. But they played them exactly once. At the end, the team scored 12 points. So I'm assuming that the top team was 12. I'm giving them any names, so it doesn't really matter. 12, 10, 9, 8, 7, 6, right? And this is a score table here. So A plays B, A plays C, and so on. And how many points are awarded for a win if a draw earns 1 point? The loss, obviously, will not earn anything. So loss gets 0 points. And now the question is, how many points are awarded for a win if a draw earns 1 point and a loss earns 0 points? This looks like a very difficult problem because there are so many unknowns here. You don't know who's winning and who's playing and which is a draw and which is a loss and all that. And they just give you this little piece of information and they tell you what the total score for A, B, C, D, E, F are. That's all they tell you. So now you have to use logic now to say how much information can I get from this? So the first question is, I'll ask, how many games were played? By the way, like for instance, suppose A uh, drew with, okay, they say how many points for A are awarded for a win. So let's give a name to this. Let uh, n points be awarded for a win. Now, for instance, now suppose A plays D and A won. So it means that D lost will get 0 points. But then A, no, I'm sorry, A won. So A will have got n points. A would have got n points because A wins and a win counts n points. That's the question. You need to know what n is. So the problem is, what is n? How many points are awarded for a win? So that becomes your unknown. But then if A won, that means D lost. So D, yeah, where D plays A, you're going to put a 0 here. So every time there's an n on this side, there's a 0 on the other side. If there's 0 here, then there's an n on that side. Okay, now, so that's an important thing. And these two will be counting for only one game, right? A plays D and D plays A, it's the same game. So if you want to count the number of games, you count only, these crosses mean that B cannot play B, obviously. So you must rule them out. And then you want to count how many games there are. And the answer is, you simply have to count how many games are played by looking at this. So there's a game here. 1, 2, A plays C, A plays D, A plays F, or B plays C, B plays D, B plays E, B plays F, C plays D, C plays F, and finally D plays E, D plays F. So therefore, and E plays F. So the number of games is 5 plus 4 plus 3 plus 2 plus 1. It's 15. The answer is 15. 15 games are played. Okay, the other way of doing it is actually you got 5 by 5. No. Yeah, you got 6 by 6, which is 36. You take out the 6 here along the diagonal, gives you 30, and divide that by 2, and you get 15. All right, because you got the same number at the bottom. Okay, so 15 games played. What other information can we have? Well, the total number of points. Right throughout is just the sum of all these. Well, that you can see. I'm writing this down. Work this thing out, 31, 52. Right. So, but what's interesting is that in this table here, I only got zeros and ones. Let me just take all these things out. Now I got zeros and n. I got various n's, and I got zeros, and I got ones for a draw. Right. But observe now that if there are n wins, suppose there are n wins altogether. No, I'm sorry, not n wins, x wins. So in other words, there are x n's here. Huh? Oh. There are x n's here. And likewise, there are x zeros here. So you'll have x n's, x zeros. So that accounts for 2x of these numbers. And the rest will be draws because it's either a win, a zero, or a draw. So you got x of these, I've got n's here, x of these have got zeros. So we accounted for 2x squares, and the remaining ones will be draws. So how many are remaining? You got 15 at the top, you got 15 at the bottom. So you got 30 minus 2x draws. Okay, so now you can actually count the total number in a different way because you got 52 is the total. And so it means now you got, if you count the total, you got n. If you had 4, 4, 4, 4, and there are n of them, so you got nx. The wins will count, the x wins, and each win counts for n points. So the wins will count for nx points. The losses will count for 0 points. And the draws, each of the draws will count for 1 point. So you got 30 minus 2x times 1, because these draws will count for 1 point. So when I add up all these numbers, I'm going to get 30 minus 2x ones, and x n's, and 0, yeah, and zeros as well. Okay, plus n 0 if you like. Now this gives you 52, because we counted the 52 in a different way also. So the total number of points is actually, you got a small equation here. You see how mathematics comes into play. You have to think now. You have to think now how many games are played and all that. And then you have to reason if there's an n here, there's a zero here. So the number of n's is the same as the number of zeros. That's a very important observation, because the number of wins will be the same as the number of losses. So you've got this equation here. You got nx plus 30 minus 2x is equal to 52. Oh God. So you got x into n minus 2 is equal to 52 minus 30, which is 22. And you have, now you got, this is a product. You got 22 is factorized here. Isn't that beautiful? So it's factorized. So n minus 2, this, we're looking for n. So n minus 2 is a factor of 22. Right? Which means that n minus 2 is one of these. What are the factors of 22? It's 1 or 2 or 11 or 22. There are only 4 factors for this. So which one is it? Now you can eliminate most of them. I'm not going to do that by arguing in a certain way. Just remember, that means n will be equal to 1, 2, 13 or 44 or 24. And you only got 15, at most 15 n's, right? Because there are 15 games. So you can't have that. And you can eliminate 1 and 13 as well. I'm not going to do that. You can see why you can't have 13 n's. And if you have 13 n's, you've got too many draws. Okay, so in the end, you'll see that n minus 2 is equal to 2. So therefore, n is equal to 4. And that's the number of points for a win. It's quite a tricky problem, but this is how it goes. Okay. Now look, I've actually exceeded my time, and I have other problems which I can still do. And this is the very last session that I'm going to have with you guys. And there's an assignment problem as well. So let me. Yeah, I got 2 more. I'm going to do these 2 problems. If you need to go, please feel free. But these are, I think these are very nice problems. I like them very much. Okay, so let's just go do this one here. Okay, 5 circles overlap in 9 regions as shown. They're very beautiful logical problems. Place one of the numbers from 1 to 9 without repetitions in each region so that the sum of the numbers in each circle is 11. So you've got 9 regions, 1, 2, 3, 4, 5, 6, 7, 8, 9. And you're going to put the numbers 1 to 9 in each one of them. But you don't know where the 1 is going, where the 2 is going to go, and so on, right? And so let's look at this picture here. But you know that the sum in each circle is 11. So when you add these 2 numbers, you're going to get 11. And here you got 3 numbers. 3 numbers here. 3 numbers here as well, but there are 2 numbers here. All right. So how do you go around doing this? So what I do is, as you can see, I've called them A, B, C, D, E, F, and so on. So you got A, E, F, and you got B, C, D, B, D, F, H in these intersections. And then here, outside you got C. So the B is that, D is that, F is that, and H is that. Okay. So how do you put these numbers from 1 to 9? All right. Now the way you do this is it requires a certain amount of thought. So you'll have to ask yourself, look, let's just look at the top three. These three together will add 11 plus 11 plus 11 altogether, right? But now, so that means you get A plus B is 11. So A plus E plus F, and then you got no. Let's do it this way. Sorry, I'm going to add the whole lot because I know that these numbers are from 1 to 9. You see, that helps a great deal. So oh, I can't see the thing. The A, C, and I here. Okay, whatever it is. Now, if you add up all the numbers, which are in these things here, A plus B plus C plus D plus all that, you're going to get 45. But then you've got 5 times 11 is 55. So where did the extra come from? The extra came from the fact that these numbers here were added twice. This was added twice, belong to those two. So the extras came from this sum here, the intersections, B plus D plus F plus H. Right? That must have been 10 because that is added to 45 to get 55. That was counted twice. So yeah, when you remove them, you have to get 45. So therefore, it's 55 minus 10. So now that's interesting because these numbers are from 1, 2, 3, 4 up to 10, 9. And the only way you can get 10 is where you're adding the 4 smallest numbers. So now the numbers 1, 2, 3, 4 are sitting inside here in these intersections, what you call intersections. But you don't know where they are. Could be 1 and 2 and 3 and 4. Okay, but that is where those numbers are. Right. Now when you look at bearing that in mind, as I started off before, when you add these three, A plus C plus I, that. When I add those shaded ones, which we know to be 10, I will get 11 plus 11 plus 11. See? Because you add the shade to that, you have these 2 shades to that, and the 1 shade to that, and then you'll get 33 because every one of them add up to 11. Right, so that means that A plus C plus I is 23. Now, this is quite a large number because 8 plus 8 plus 8 is 24. So you know that 7 plus 8 plus 9 is 24, right? Those are the 3 largest numbers, but you got 23. So how can you get 23? You have to reduce the 20 is 1 more. So you can only get 23 by 6 plus 8 plus 9. Just reduce 1 from each one of them, or 7 plus 7 plus 9, or 7 plus 8 plus 8. And just keep reducing this. That's the only way you can get 23. But you're not allowed to have this because no number is repeated, right? So that is out. That is out. So A, C, and I are 6, 8, and 9. So this is 6, 8, and 9. But you don't know where they are. It could be 8, 6, 9, 9, 8, 6, or whatever. All right. So now here's the next piece of logic. If A is 6, then this one here has to be 5. And that's not true because the shaded parts are only 1, 2, 3, 4. Right? The shaded parts. So A can't be 6. Because A is 6, then B has to be 5. And we said that those shaded parts are 1, 2, or 3. The same argument holds for I. So the I is not equal to 6 as well. But this one you shares with 2 others. So this could be 6. So the middle one is 6. So straight away now you've got something. So that is 6. All right. So you got 8 and 9 in these 2 places. All right. So what's the next thing to do? We don't know which is 8 and which is 9. But it doesn't really matter because if we put 8 and 9 here, then I put 9 and 8. It's just the same thing reversed, right? So let me put 9 here. Okay, so I can put 9 here and 8 here. So I've got 3 numbers now. Those 3 added to 23, and we saw it has to be 6, 8, and 9. All right, so if that is 9, so this part here will have to be 2. So we're getting somewhere. Well, let's just take out all these shades, you don't really need them. So this has to be 2, and this has to be 3 here, because they add up to 11. So the 1 and 4 go in here, right? So now you can try 1 and 4 and see what the things are. But what you notice is that I can't have 4 here. If I have 4 here, then 4 plus 3 is 7, and this will be 4, you see, because these 3 add up to 11. I can't have 4 there. So I have to have 1 there. And once I do that, then I've got the rest of the things filled. I can't put 4 here, so I have to put 1 there. Because this is 3, we already know. 1 and 4 go here, so I have to put 1 here. And then after that, the rest of it follows. You got 1 plus 3 is 4, and I need to have a 7 here. And 6 plus 1 is 7. So this has to be 4. We said it's 4 anyway. 2 plus 4 is 6, 5. Perfect. You got all the numbers from 1 to 9. Yeah. So with a very, very little minimum information, we're able to solve that problem. And the final problem, last one that we are doing, they say all the positive integers greater than 1 are painted 2 colors. And this is a typical kind of an Olympiad problem. Are painted 2 colors, but all the integers. So 1, 2, 3, 4, all the way. There are only 2 colors, right? It is known that the sum of any 2 blue numbers, let's put it like this, b plus b, the sum of any 2 blue numbers is blue, including the sum of 2 equal numbers. All right, so 4 plus 4, for instance, if 4 is blue, then 4 plus 4, which is 8, so that's also blue. And the product of 2 red numbers is red. Right? That's all they are given. It is also known that the number 1024 is blue. And there is at least 1 red number. R is at least 1. They ask you how many numbers greater than 2000 and less than 2024. That means from this lot here. Greater than 2000, less than this. How many of these are red? So in other words, we have to identify every one of them to find out whether they are blue or red, right? Okay, the starting point is that 1024 is actually 2 to the power of 10. It's 2 times 2 times 2, etc. So what does this mean? It says here that suppose 2 is red. Now the product of two red numbers is red. So it means that 2 times 2 is red. Now this is red. If I multiply this by 2, that's also red. And if you keep going like this until you come to 10 of them, so this will be red. But it's said that this is blue. So again, it's a proof, let's say, proof by contradiction. If you assume 2 is red, you'll end up with 1024 being red, not blue. So therefore, the conclusion is that this supposition is false. So 2 is blue. Okay, so now we've come to the conclusion that the number 2 is blue. So let's just make that conclusion and say, we know now that 2 is blue. If 2 is red, then 1024 is also red. But they say blue plus blue is blue, right? So it means the 2 plus 2 is blue, and 2 plus 2 plus 2 is blue, and so on. In other words, the sums of many 2's are all evens. So all evens are blue. So it means all these numbers here, 2002, 2004, and so on, all the way up to 2022, they're all blue. But they ask how many of them are red. So now we don't know about the other numbers now. You know, the odd numbers in between. Maybe there are some of them are also blue. We don't know. We know these are blue. It could be the others also. Some of them are, the others are blue. All right. So how do you attend to that? Okay. So I'd like to prove now that all the odd numbers are red. Then I will be able to count it easily. Okay. So let me try to prove that all odd numbers are red. Let's start with 1. I'm going to prove that it's red. So I'm going to assume that it's actually okay, I'm going to prove that all odd numbers are red. Let's start with 1. I assume that 1 is blue. Oh, but then you're going to get everything is blue. The reason being that if I add 1 to 2, which is blue, if I add 1 to any even number, which is blue, then I'm going to get all the odd numbers, you see? So that means all odds are blue. But all the evens are also blue. And that means all are blue. But it is said that there is at least one red number. See how that information becomes useful. So this is false. Because we just proved they're all are blue. So then 1 is not blue. That assumption is false. So therefore 1 is red. Right. Okay. Now let's take any odd number. I want to show that all odd numbers are red. So let n be any odd number. I want to prove that n is red. We want to prove that all odd numbers are red, right? Okay. Now, here, I'm not going to prove it by contradiction. I'm going to prove it like this. That means n minus 1 n is equal to n is an odd number. N minus 1 plus 1. Oh, yeah. So actually, I needed to show that 3 is blue. Okay. We can take 3 to be blue. Okay. Assume 1 is blue, it's false. 1 is red. And the same thing, if 3 is also red. If 3 is blue, you get a contradiction. You prove it in the same way. 3 is also red. So you have that n is equal to n minus 3 plus 3. So what you have here is that the n is odd. So odd minus 3 is even. So this is blue. And if 3 is blue, then you have that n is blue. So yeah, so this equation here tells you, well, what's the logic here? I'm sorry, I'm losing it. If you have, you can prove that 3, yeah, no. So your assumption should be is n blue. Yeah, sorry about this. Suppose n is blue. I'm sorry. So take any odd number and assume it's blue, or assume that there is an odd number which is blue. So suppose some odd number is blue. And then you can prove that any odd number greater than 3 is blue. If n is any odd number, then n is equal to n minus 3 plus 3. Or if you like, yeah, and if n is blue, so n is odd, so this is even. And oh boy. All right, look, I'm going to stop here. But you can use this argument to eventually get a contradiction. Try it. We've done enough examples on contradictions to figure out how it's going to work. So I'm not going to waste your time because Kotso is already, is way past his time. He's helping us. So you get a contradiction here. If n is any odd number, and you suppose that it is blue, if there is some some odd number which is uh, which is blue, then you get a contradiction. That is the assumption. Assume that there is an odd number which is blue, and you get a contradiction. So therefore, there is no odd number which is blue. So all odd numbers are red, right? Which means that all the odd numbers in between here are red, and you can count the number of red odd numbers very easily because you know the even numbers there are blue. So you can count them. So the idea is if there is some odd number which is red or blue, then you get a contradiction, and therefore all odd numbers are blue. Okay, thank you for that. And this last problem here is on a clock. Your assignment problem. If you got time, you have to do this assignment. And the assignment, I've got it written here. It's about the clocks. It's a clock problem. Okay, I've done one clock problem, so that should give you some idea of how to tackle these problems. Uh, yeah, at midnight, the hour and the minute hand overlap. And the question is, at what time do they overlap again? Well, very often, the minute hand and the hour hand overlap as it goes round and round. It keeps overtaking it. So at what's the next time when they will overlap? You can try that. That's not so hard. Uh, and all the best. Thank you very much, guys. And this is the last time I see you. And hopefully, let me just see who's left here. I still got 18 people, which is very nice. Uh, okay, thank you for coming. We started on time, so some of you came a little late. Uh, thank you very much, guys. I don't know. I don't know what your faces look like, and uh, I can show you my face. Oh, okay. So what's going on here? There you can see me. I can make a full face. I don't know. I don't know how to do all these things. But I have been talking to you for 10 sessions altogether, and I wish you all the best. Right? If you were following me right through, undoubtedly you will get a distinction in metric mathematics because metric mathematics is trivial as compared to what we were doing, and hopefully you will get over 90% uh, and get a place in medical school or actuarial science or whatever you want to do. And at the same time, as a side thing, you can take part in the Olympiads and get trophies and score marks in it. Okay, if you do all the problems that I have done, and if you know how to do it, do them by yourself, I can guarantee that you'll get to the top 100 in your round three. So everything is recorded. So if you are keen, if you really want to get to the top 100, so that you have a lovely certificate to show off when you're applying to higher institutions, then uh, when the holidays come, go over all those problems and try to do them yourself so that you are quite familiar on the different techniques that you use to solve these problems. Thank you very much. Right, and we'll close up now. Okay, I think Khotso has stopped the recording, and I think he's left. Yeah, I think Khotso has left. Okay, I really taxed his patience there. Khotso, are you still there? No. All right. Okay then. Bye, and everything of the best. Thank you for coming. Yeah, I probably will want to have some classes at some point or the other, and hopefully your email addresses have been given to Kotso. If you can, if you want to attend any of the other sessions, which I will do outside the South African Maths Foundation, because I give a lot of interesting lectures on Fibonacci numbers or the regular pentagon or something like that, some number theory, then I might just feel inclined to give a special lecture on that. I might even give a lecture on high school mathematics, graphs, or something like that. So please send your name to me. Maybe you better send your name to me. Uh, my email address is, let me just quickly uh, share this email address with you. Mm, if you send me your email addresses, then I will send you an invitation whenever I have a special class. Okay? Hmm. I think Kotso is gone, so I can't really share. But just you can write this down. It's Pillay, Pillay. Maybe I can put it in the chat column if that is still alive. There's PILLAYPH at ukzn.ac.za. So there it is. You can see it in the chat column. PH at ukzn.za. Write that down and send me your email addresses. And whenever I have anything special, I'll invite you to a Zoom session and you can come and attend. Right. Now there's a note here. It says just a quick update regarding the December camp. To qualify for selection, you need to have submitted at least 6 assignments. Okay, they've been a little bit lenient. Missed no more than 3 sessions out of the 11 we've had. Please note, meeting the minimum requirements doesn't automatically mean you'll be selected. Learners who submitted all assignments will go and attend all sessions will be given first preference. So it all depends on that. And for those who join the program later, don't worry, we'll only consider the sessions as part thereof. Okay, so there it is. You got a notice there. Submit your assignments, and you will be in for the lucky draw to go to the December camp, which is in the University of Stellenbosch. So you'll get a free ride to Stellenbosch, I think, and you'll get 6 days of additional instruction to train you to, and then they will choose